Hey 8th graders, this video is mainly for DLI kids, but if you were absent either Monday A-Day November 23rd or Tuesday B-Day November 24th, you guys will use this video to help you guys navigate the Newton's third law dynamic cart lab. So in class we'll be doing this lab with the dynamic carts, but everyone else who's working from home will be watching this video and another video to figure out how to collect data for the dynamic carts. So basically what a dynamic cart is you guys can see it in this picture up here, is a little cart with wheels, and then it has this little metal ring. And those two metal rings will show us how much force is put on each object in a collision. So if we were to collide those two cars, you guys will see that the amount of bend in those rings on the front of the cars is going to equate to the amount of force that they have in that collision. So the big thing that we're discussing with this is Newton's third law that states that for every action there's an equal and opposite reaction. Okay? That's kind of the general way of putting it, but I don't like to define Newton's third law as that. The best way I would define Newton's third law is when you have two objects collide, okay, no matter the size of the objects, whether you guys have a semi and a smart car, okay, when those two objects collide, they put the same amount of force on each other. So the semi puts a force on the smart car, but even though that smart car is teeny, it puts an equal force back on the semi, but in an opposite direction. That's something that I think a lot of kids have a misconception about, is like, all right, well, the semi is larger, it's going to put a bigger force on the smart car. That's not true. And these dynamic carts will show you that. So what we'll be doing is messing around with the mass of these dynamic cars and then causing them to collide. And you guys will see that no matter what mass of these collisions, you'll see that the rings will compress for both on the same side each time, okay? So even if this car is heavier than this car, when they collide, they will compress the same amount. And again, that shows us the force of that collision, okay? I think that why this is a misconception for a lot of kids is because they see, all right, a semi and a smart car collide, okay? When they collide head on, that semi is going to keep moving forward. It maybe slows down a little bit, but it keeps moving forward. However, that smart car gets completely shot off in the opposite direction. Okay, because they have a different mass, and we can look back on Newton's second law, but because they have a different mass, they are going to respond differently. They're going to have a different change in velocity. So they have the same force that occurs to them, but they're going to have a change in acceleration based on their mass. So again, that goes back to Newton's second law. So I'm just going to do this first example for you guys, and I'm going to show you the video that you'll be using to collect data. So the first part of this video, okay, you guys can see cart A, cart B, and you guys can see number 1 as well. Okay, so this one right here is number 1. Okay, so cart A is going to collide with cart B, and both of those carts are going to be going the same velocity and have the same mass. So we haven't added any weight to either of those carts. What you'll be looking for as far as observation goes is comparing the bend in the rings. So you'll tell me what the bend in the rings look like for each of those carts. If you guys are doing this right, you should get the same answer for all of these. Okay, and then after they collide, what does the change in the velocity of cart A look like? You guys obviously aren't going to give me a number for velocity, you're just going to give me an observation. And again, same thing, change in velocity for cart B. Okay, so let's go ahead and watch this first collision. It's in slow motion, so you can really see how the rings in the front compress when they're subjected to a force. Okay, so again, both have the same mass. They are roughly moving the same velocity towards each other. But if you look right there, okay, even though they didn't quite hit head on, you guys can see that they have the same compression. So that means that this cart is putting a force on this cart that's equal to the force that this cart is putting on this cart. Okay, so on this first one, you would write comparing the bend in the rings compress the same. Okay, and then the change in velocity. So after the collision, you're going to look at this and see what happens to the change in velocity. Okay, so for this one, change in velocity of car A, that was the car on the left, you would say moved backwards at the same speed as B. Okay, cart A, because it had the same mass as well, also moved backward at the same velocity as C, or excuse me, A. Some little typos there, okay? And then that's basically how you guys fill out the data for this. I'm going to show you guys just one of these, one more of these. So let's go on to question 3 where we add a weight. So now we're going to look at mass. And this one says cart A is moving towards cart B. Cart B is going to be at rest and have a 3-pound weight. So if we go back to our video, I'm going to kind of just skip forward to 3. And you guys can move through these as you need by just clicking and dragging. So let's just look here and pause once they collide. So you have a little bit of the book covering it, but you can see that this compression is the same as this compression. So that means that even though this textbook is heavier, it's still getting the same force as A is putting on it. So cart A is putting a force on B, and even though this one's heavier, cart B is putting a force back on A. And then you guys can observe what happens. This one was stopped, this one was moving, so after they collide, okay, what happened to cart B, what happened to cart A? Okay, so that's your guys' lab for the day. Pretty simple. Again, pause that video as much as you guys need, and then you guys will answer these 2 questions. DLI students and any absent kids, you guys have this one right here. You guys can make a prediction and put on there what would happen if both cart A and B had a weight. So then you guys can say, all right, what's your prediction on this? So actually, you know what, let's do it this way. I remember what I wanted to do, sorry about that. So you guys are gonna make up your own, if you guys could do this in class, what would you test? That's what I want you guys to do. If you could do this in class, what would you test, and make your prediction on how you guys think this would respond. Okay, so it should be different than one of these other ones. Again, you guys could add more weight, you guys could change velocities, stuff like that, but go ahead, type out what you would do if you were doing this in person and make your prediction right there, and then answer these questions. How does the strength of the force exerted by cart A and on cart B and the force exerted by cart B on cart A in each collision compare? So no matter what collision, how do those 2 forces that they're putting on each other compare? And then give a specific example from lab. So what that means is you're going to look back from your data and say, all right, on number 2, this is what I saw happening. Okay, and give me your data from that. Explain it a little bit better using data. Question 2, why do the results after the collision look so different for cart A and B in certain scenarios? So if you're looking at the velocity after those 2 collide, why are they so different in all these scenarios? Okay, and again, give a specific example for lab. So tell me about, like, maybe, oh, on 3 it did this, but on 2 it did this. Okay, and then finally, how does the direction of the force exerted by cart A and cart B, by cart A on cart B, and the force exerted by cart B on cart A in each collision compare? So now we're looking at the direction. So what does the direction look like when A puts a force on B? And what does the direction look like when B puts a force on A? And then again, what specific evidence do you have? So when you guys are done with that, you guys will turn this in on Teams assignments, and you are good for the day. I hope you guys all have a great day, and I will talk to you soon.